All right, so let's go on to this other approach that's been recently popularized by Scott Jasheko, and that is to use lakes as an integrator of large-scale patterns of evaporation and transpiration. It's kind of a complicated slide. It's just sort of the introduction to this. The paper, and I'll talk about kind of how it works, is that within the hydrological cycle you have drainage basins, and in many of these the drainage basins fill up lakes, and the lakes are carrying the isotope ratio value that's being impacted by evaporation processes and transpiration processes in the watershed. So the idea here is that you could use a lake as the isotope ratio value of a lake and its isotope ratios compared to precipitation to estimate the proportion of evaporation and transpiration for an entire drainage basin. Quite clever and very interesting. Would be a very, very useful approach because many of the other approaches that I've shown you are sort of point scale measurements using isotopes that are difficult to scale up to large landscapes. And so this was very attractive, and is very attractive still, as a way to characterize the evaporation and transpiration differences for entire basins. So you can imagine that in soil surfaces within the basin, there's water that's evaporating, leading to the enrichment of the heavy isotopes, and then as you get more rainfall, that signal moves into the groundwater or runoff, and that evaporation signal gets pulled into the lakes, and you can measure that effect within the lakes as an integrator. And from the study, well, that's just what I said, but they concluded that at a global level, that transpiration accounted for above 80% of the total evapotranspiration across terrestrial surfaces, which if you work in arid and semi-arid basins, you're thinking, no way, that's really, really high, because we're used to values of 40 and 50% of the total ET being transpiration in some of these systems. So it seemed really high for most folks that study evaporation and transpiration. And so we considered that there might be some assumptions in how you apply this approach that need to be addressed a little bit more carefully. For example, how well does the lake integrate all the processes that are occurring within a basin? You can imagine that there's some level of decoupling between the water that's moving from the high precipitation areas and maybe preferentially represented by the high precipitation areas versus the lower basins, which are not leading to some drainage into the lakes. So the lakes may be not even characterizing the whole basin. They may be only characterizing parts of the basin because of this sort of decoupling that's going on. And you can also imagine that there's evaporation signals that might not be picked up with the groundwater drainage or runoff because of some other decoupling processes at a local level. And I'll talk about those. And so we took a look at this for some of these assumptions in a paper we published the next year from some data we collected in Wyoming. And what this shows is the hydrogen and oxygen isotope ratio value for different water pools and fluxes within a mountainous system, snow-fed mountainous system in Wyoming. And you can see the snowfall signal has a quite low isotope ratio value because it's cold precipitation. Rainfall is quite a bit higher up on the right. And all of the groundwater and runoff signals that were measured in this basin showed no effect of evaporation enrichment of the heavy isotopes. In other words, the runoff and groundwater signals that we continue to measure in these systems show no effect of evaporation enrichment of the heavy isotopes. But that's one of the main assumptions of the Jasheko paper, is that that signal gets incorporated into the runoff into the surface or groundwater and collects in the lake, such that you can then extrapolate the evaporation and transpiration processes for the entire basin. But we're not seeing it here. Knowing that there is quite a bit of evaporation off the surfaces from these mountain catchments, but it's not being captured here. The isotope ratio value of Wyoming streaming groundwater falls right on the meteoric waterline. And the only values we were able to measure in this system that showed any kind of evaporation effect were in the lakes themselves, suggesting that all the evaporation signal is occurring in the lake, but not capturing the runoff or not capturing the evaporation processes in the drainage basin. So we didn't see it. Another thing that we noted in this paper is that sublimation from snow, which is really important, leads to, in many cases, no isotope effect on the snowpack and thus the movement of water into the lakes. So here's a whole missing component of the return of evaporated water or sublimated water to the atmosphere that, at least in our cases, is not showing any isotope effect. So what this figure represents is a time course of the cumulative water vapor flux, which is the solid line. And the winter period is in blue. And just note here that about 50% of the water that's returned to the atmosphere from these mountain catchments in the Central Rockies, at least from our site, is sublimated. Okay? Occurs during the winter time. So that's a lot of water loss from the snowpack back to the atmosphere. And if you look at the diagram in the bottom right, that shows the darkened symbols are the snowpack isotope ratio values. And despite that, there's so much sublimation returning back to the atmosphere, we don't see any kinetic isotope effect causing the values of the snowpack to deflect off of the meteoric waterline, which is necessary if you're going to pick up an evaporation effect on the landscape. It's not happening. So it's interesting. I mean, one would expect that sublimation is like evaporation, requires more energy, in fact. There should be an isotope effect of sublimation on the snowpack, but we're not seeing it in this system. And so this paper was to kind of argue about some of the assumptions of the Dusheko paper, suggesting that maybe you can't use a lake as a perfect integrator of processes throughout the basin. I think you have to be very careful in applying that approach. And about the same time we published our paper, Scott Dusheko and Bill Schlesinger wrote a paper noting the bias of their method in partitioning evaporation and transpiration from the basin. And the isotope method that they're referring to that's shown on the far left of that panel is this lake integration method compared to other methods for partitioning E and T across the landscape, which show quite a bit lower estimates of transpiration as a fraction of total evapotranspiration. So that's a nice thing when you write a Nature paper, then you can write follow-up papers to, correct what you wrote about. And I'm just kidding. Scott's a great guy. He's doing some great work. Okay, so those are take-home parts for section 3. Any questions about using lakes as an integrator of evaporation and transpiration? Caution, yes. Yeah, and they account for that using a lake-water balance model in the Dusheko calculations. So they account for the water balance, the precipitation inputs. They use a local meteoric waterline for precipitation inputs. They did their job really well. I think in the end, it overestimated the proportion of evaporation the proportion of transpiration to total ET, because the lakes are apparently not capturing all of the processes that are occurring out in the basin because of some of these decoupling factors and also some of the factors that aren't leading to strong isotope effects like the snow sublimation. Turi and then John.
It would seem you could think about this in a whole large scale just by including a mixing phenomenon. In the nice piece of that is the snowpack is not mixed.
Yep.
So you're only just taking it off the top.
That's right.
Within a lake, you have mixing,
yep.
And so that allows the fractionation to take place on the cumulative scale.
Yep. Was that your question?
Same thing I was going to say.
Okay. Well, I want to show you the next slide then. That's what we're trying to understand, is sort of the isotope metamorphosis of the snowpack.